links in case you want to rewatch some. Yes, thank you. Good. Choosing and reporting of statistics. So I'm not going to go too deep into the topic. So Nolan and Heinzen shows this according to Airbnb estimations. I'm not going to go too deep into that. I'm actually not going into this at all. But what I want to show you is this decision tree. So you called it a decision tree. And this is decision trees are also nowadays you have them in various contexts. It's usually you make decision based on probabilities, and you basically follow this probability tree down if you use them statistically. Here it's really more for you to understand where do you come down in terms of the different levels. So when you have, so there are 4 different categories. So you have only scale variables. You have a nominal independent variable and a scale dependent variable. You have only nominal variables, or you have only ordinal variables, which we didn't do. So this is actually to be seen detached, but it's part of the chapter. So know the answer and know where to find it. So we remember when we have scale variables, we're asking questions about associations, and we will ask questions about predictions. So if you're only interested in the associations, you look into Pearson correlation coefficient. So basically, we will talk about it in the following. So basically, you are testing for associations, and you're statistically testing for these associations. If you want to predict something, you're using the insights from the correlation to basically use your standardized X to predict your standardized coefficient Y hat. Then you have the case where you have a nominal independent variable and a scale dependent variable. So this is where we're going a little deeper. So then the question is, do you have 1 independent variable, or do you have 2 or more independent variables? And again, just because we didn't do it and we didn't do the calculations how to do them, I still would like for you to know that as soon as there are 2 or more independent variables involved, you need to think of a 2-way or more way type of ANOVA. However, we only did with 1 independent variable with several levels. Essentially, it's 3 or more levels. So this is when you think 1-way within groups ANOVA, when you have the same individual going through the same levels, or you have a 1-way between groups ANOVA if you have different individuals in the different levels of the independent variable. Then you have with 1 independent variable, you could have 2 groups, which is, now we're going back to t-distribution. If it's only 1 sample, and you're comparing that 1 sample to a reference value or to a population mean, you basically have 2 possibilities. You have the mu and the sigma, which is the population mean and the population standard deviation. Keep those apart. I've seen that on the quizzes. Some of you have made mistakes there. Greek letters indicate population parameters. Statistics from a population are called parameters. So mu and sigma are parameters. And if you have them from a sample, they're basically called statistics. And then it's an S or an M or an X bar, or then in the following an SEM or a sigma M, a standard error of the mean. So when you have sigma and mu known, and it's being provided to you, and that will prompt you to think SAT test. And if you're prompted to think SAT test, you think of a SAT score table. Don't use the t-score table. The t-score table you use when you only have the mu known, and you need to estimate the sigma. And you're estimating the sigma by computing S, the standard deviation. And you're doing that slightly different than you would do it in a population, because you're dividing now, you're dividing your sum of squares, which is basically to get to the variance, you're dividing the sum of squares now not by the sample size as you did for the population. On the population level, you're dividing it by your degrees of freedom, which is the sample size minus 1. That's this arithmetic manipulation to basically make this a little wider, that standard deviation estimate. So you have a within groups design, you have a paired sample t-test, you have a between groups design for 2 samples. This is the continuation of the STAT process. So you're estimating that standard deviation from the population by basically using your sample standard deviation. If you have the same individual undergoing through the 2 different timely conditions or 2 different test conditions in whatever shape or form, but there's always kind of a before or after, some chronologic dependency involved, then you would think paired sample t-test. If you have 2 independent groups that you're comparing against each other, then you think independent sample t-test. Make sure that you understand what's different between those calculations, because for an within groups design paired sample t-test, you're basically, your degree of freedom becomes the number of differences minus 1, which means it's those pairs, those paired data. So you basically have before and after. So you have 2 columns and you calculate the difference. Your degree of freedom is the number of measurements in both conditions and the difference of those minus 1. Whereas in independent sample t-test, you're basically subtracting minus 1 for each group. So you have a different degree of freedom. You have a degree of freedom for 1 group and degree of freedom for 2 groups. Overall, it's the sample size of both groups together minus 2. So those are trick questions which I've seen some of you trip into. Then we have the one-way within groups ANOVA and one-way between groups ANOVA. We talked about that. Then we have the 2-way between groups ANOVA, which essentially is then the advanced format where you have 2 independent variables. You're dealing then with interactions, which makes it a whole different, more complicated conversation. Then you have the situation where we have 2 nominal variables. You basically have 1 nominal variable, and that would prompt you to think of a chi-square test for goodness of fit. So that's the simple one. Remember the soccer players, early in the year, later in the year, elite soccer players in Germany. Then you have the more complicated scenario where you have 2 nominal variables, and there think of our paper cup examples, right? So you have trash and recycling as the outcome variable, and you have the independent variable being, is that cup labeled with your name correctly? Is that cup labeled with the name misspelled? Or does it have no name on it and all? So think of these 2 nominal variables. Think of the 2x2 or 3x2 table that we did for our paper cup examples. And then we have the case where we have ordinal variable. Keep in mind the different types of variables. So you basically have continuous and categorical variables. Continuous variables can be intervals or ratio, with ratio having a meaningful 0, meaning there is nothing less than 0. Think of the cookie example, right? So how many cookies are left in the jar? What's the temperature of the cookie? Can also take negative values, and 0 is just a random number. Then you have categorical variables. You can have, so what type of cookie is it? Or the ordinal variable, which is my favorite cookie. Keep in mind that the actual order, the presentation of orders, let's say chocolate chip is my favorite, oatmeal raisin is my second favorite. So that's the ordinal variable. When you're actually using it and you're using ordinal variable to count how many cookies do I have of my least favorite cookie and how many cookies do I have of my most favorite cookie, that essentially is then a ratio variable and not an ordinal variable. So if you're counting it and the variable becomes the count, then it becomes a ratio variable. So it really depends on how you're employing your knowledge. Okay, so keep that in mind about ordinal variables. So when you have questions about associations, so Spearman rank or the correlation coefficient, that's the non-parametric brother of our Pearson correlation, which basically only deals with normally distributed data that is scale in nature. The Spearman rank or the correlation coefficient, basically it ranks each data entry and it correlates this rank. So you basically have 2 variables, and you have one variable is absences from class, and the second variable is exam grades. It basically creates for both of these variables ranks, and it ranks them from highest to lowest, and then basically creates a correlation of the ranks. And by doing that, you basically get an idea about how tightly are these two correlated, these two variables. Whereas if you remember the Pearson, we basically associated the actual values and not the ranks. So but that's Pearson. Spearman is then basically a way to use it without needing any assumptions about the distribution of the population, which is one of the conditions of our parametric tests, right? Then we have between, did I go record now? Yeah. Okay, oops. Oops, what am I doing? And lastly, we have a nominal independent variable and ordinal dependent variable. So if we have within groups designed in two groups, we would use a Wilcoxon signed rank test. So the Wilcoxon is basically the non-parametric brother of a paired sample t-test. It again creates a signed rank, and it basically again uses the ranks, and thereby circumvents the problem of the data not being normally distributed. If we have a nominal independent variable and ordinal dependent variable, we have a between groups design, which is with two independent tests used as a Mann-Whitney U test. I'll spare you the details on this test, but it's the non-parametric brother of the independent sample t-test. And then you have the non-parametric brother of the ANOVA, where you have 3 or more levels of the independent variable. That's the Kruskal-Wallis H-test. So just know where to get this information from. That's why I like this slide, and that's why I always show this slide. And that's, I think it's a very useful slide, because you will likely face, if you continue your education and you're exposed to statistics or research in some shape or form, you will need to make decisions on which tests to use. You may not need to know how to use them, but you may need to guide a statistician, or you may need to have a conversation with a statistician on what to use. And I think this conversation is quite important to have, and it's important to know the proper terminology when you have this conversation. Good. So I'm highly flagging this table for, like, make a mental note and maybe print it, even put it on right next to you when you're tackling those questions on the farm. So again, so now we're just walking through. So Pearson correlation coefficient, we will talk about it once we get to the chapter. We're quantifying it. We're comparing its magnitude to Cohen's conventions, which you will find on your canvas today. Cohen's convention, and there were some issues essentially on the quiz, and I've given you the points, and I posted today the overview of this effect size problem. So it's the effect size is, these conventions are not really clear science. That's why I actually disagree, and I have taken out most questions that deal with this kind of, was classifying the conventions, like giving you one value and saying, okay, so is this a medium, large, or small? Because it's not really exact science, and I'm not sure that's really a necessary question. But nevertheless, you need to understand kind of the ballpark of in which these effect sizes are operating when you look at them. So the conventions per se are still important, but classifying one effect size to a certain is not really necessary, particularly if you have something like minus 0.47, as I've seen once. And is this medium, is this large? And then you have to think whether it's lower or whether it's higher. It becomes a little, I don't know, ambiguous. But yeah, but I've posted this PDF to Canvas for you to have it in front of you if you need it on the final. So you have the Pearson correlation coefficient that basically determines the strength of association in a correlation. And then you have a prediction. The prediction was the outcome of a regression equation that then basically allows you to establish predicted dependent variables using the correlation coefficient and the standardized independent variable. That's your standardized dependent variable that you can then convert in the knowledge of the standard deviation to your actual raw predicted y. So then we have scale-dependent variable. We talked about this. Also, maybe go through these in a little bit. So we talked about it already. So you basically know what the number of samples you're dealing with, Z-test, T-test. You have two sample distribution. Your comparison distribution here is the distribution of means. That's what you use for a Z-test. So that's the distribution of means. Here is also the distribution of means. Here's the distribution of the mean of the differences for independent sample t-tests. You remember the two samples. You're taking out random subsamples. You create a difference. You're dropping them back, and you only keep the difference. So the comparison distribution here is the distribution of the differences between the means of your subsamples. With the ANOVA, your comparison distribution is the F distribution, which basically is a unimodal right-skewed distribution, where you basically compare the calculated F, which is variance between, over variance within. Basically gives you an F score that essentially allows for you to see then whether at least one pair, so one group is different from another group, as the null hypothesis says that they're all equal. Same with the within groups, but the difference with the within groups is that you take the intra-subject variability out of the equation. You're removing this from your estimate, from your variance, and thereby you actually get a more detailed estimate of the variabilities and the differences in the variabilities between the groups by subtracting the subject variability. Yeah, how to name an ANOVA? We know that one way between groups, within groups, a mixed design. We didn't do mixed design, we didn't do three-way, but it's basically all possible. Particularly when you have three-way, you can easily have a mixed design where individuals go through several conditions, levels of the independent variable repeatedly, and so they go through all the levels. But for the overall comparison, there's then another level that makes it a three-way that basically does not. That basically is a between groups design for the different levels. So you have one way, two way, three way, between, within groups, and mixed design, and all of it is analysis of variance because you're comparing the variances between the groups in relationship to the variances within the group. When research design has only nominal variables, we have two choices. If it's only one nominal variable, which is basically the count of elite soccer players in the respective time of the year. So there's only two levels of that independent variable, and you're only comparing these two levels. So that's one nominal variable. Then you choose chi-square test for goodness of fit. If you have two nominal variables, we choose the chi-square test for independence, which is paper cup example, 3x2 table. And we're determining whether there's an association between the dependent and the independent variable. So also the null hypothesis is from a chi-square test is that there's no association between the dependent, the outcome variable, and your independent variable. And you're testing whether there's an association by comparing the observed counts in each of these cells minus the expected count. So remember, the formula is square root of observed minus expected squared divided by expected. So you're creating a ratio between that difference squared divided by the expected. So that's correct. Also kind of have an understanding about how to report statistics, so and know where to get this information. And that's maybe more of a take-home message than something that will be tested on the quiz. So there are different, how should I say, resources. So these are the more psychological resources from psychological associations. So the APA has standards on how to report research. There's an article writing quantitative empirical manuscripts, Rico and Flair. Yes, it's possible. There's also, for those that are going into medicine, there's an excellent book called How to Report Statistics in Medicine. An actual book, actually a British medical journal is publishing that. In addition to that, I also want to briefly show this. What am I doing here? Also, I want to quickly show you the so-called equator network. There's nothing to do with the globe, but the equator network is enhancing quality and transparency of health research. And you remember how we talked about different study designs, right? So you have different ways how you approach data, and they have guidelines for each individual study design. And when you look at these guidelines, so I do a lot of observational studies in epidemiology. When you look at these checklists, they're kind of very transparently showing you what you need to write into your paper to make this transparent and presenting your data with a logical flow. So these are all the bullet points that need to be touched upon in your paper. I'm flagging this because all of you are going to write some form of paper at one point in time during your education. You may also write thesis. And if you write thesis, these points all need to be attached and addressed. I would even go as far, and I'm doing this with most of my submissions when I submit papers to peer-reviewed journals, I would go at length to add such a strobe statement as a Word document with each bullet point explained where in my paper they find this information. Because if you have this reviewed by 4, 5, 6 peer reviewers, or in your case, professors that are reading your thesis, or maybe if you're going to research later on, also peer reviewers, you're doing them a favor because they know that you have thought of that. So I'm presenting you the psychology of it. So you kind of you're taking, you know, how a reviewer wants to find something, you're taking a lot of wind out of the sails of somebody wanting to find an error in your work. But that's just a little bit of a background to reporting. So, but these resources definitely useful resources also know how to report, let's say, a difference with a p-value, a t-score with a p-value. We've done this in when we talked about t-distribution. So there's just know that there's the t equal and then a semicolon, and you have the p-value following right after. So there's just a standard convention of how to report data. So also you will basically, when you do statistics and you do analysis, so paper is always structured as an introduction, background, then you have a methods part and you have a results part, and then a discussion, and most likely followed by a conclusion. Or you have discussion and conclusion together, different requirements from different journals or submission platforms. So in the method section, you need to indicate pre-registration. You need to present your study design, how you designed and why you designed it that way. That includes a sample size and the power calculation if you did it. Then you have a statistical analysis part in which you're basically outlining what you did and how you did it. That includes stratification, grouping, categorization. So categorization in a way of the so-called discretization, which we're going to talk about in a second. And then the results section, you describe your analyses from both traditional hypothesis testing and the new statistics. What does that mean? New statistics, remember, always present effect sizes and also always present confidence intervals. So you always need to have some estimate of variability in your data to basically make this as transparent as possible. So researchers will justify the study by pre-registration. So pre-registration, we talked about transparency of research, and transparency of research basically is at the highest level if you have a predefined study design, predefined analysis, and you're stating all of this already before you even approach your first patient. And that's really how it's done. In the end of the day, many research grants essentially are given to protocols that sound promising. So you need to know how to design a study and understand the design of a study to write your own grant proposals, review grant proposals, understand pre-registration websites. And I showed you clinicaltrials.gov, where you see a lot of these designs outlined. So the justification of the research need and the research approach chosen by the researchers will then be part of this pre-registration. You summarize 4 items in the method section: the pre-registration, yes, including the clinicaltrials.gov number if you have pre-registered it. Then you have the power analysis. Then you have outlier, how you dealt with outlier or how you plan to deal with outliers if you write a protocol. Because outlier, there's a good chance you will have outliers, and what are you willing to accept in your data, or what are you a priori discarding because you think this is an outlier based on some analytical or pre-analytical error. So all of this should go in a method section. The psychometric data for each scale used. So you should have an estimate of reliability and validity of that test that you're using. So if you do a psychometric assessment, you will need to go back to the literature and you will need to find data of validity and reliability. And you will say, okay, so I found this XYZ survey. I think this is a valid and reliable tool based on research done by XYZ et al. And colleagues from that university. So you basically reference your method. So the reporting of the traditional and the new statistics are hypotheses and tests. Basically, you state your hypothesis. Can go even as far if you want. If you have very complex hypothesis, you can even say null hypothesis, alternative hypothesis. That's what I was testing. That was my primary hypothesis. You state your assumptions in the light of the methods, then basically provide your traditional findings, which is a difference and the p-value, but then also add your new statistics and add the effect size of the difference and in the light of the variability, and also add a confidence intervals. So know how to use graphs and remember how graphs are called. So this, for example, this is a so-called Venn diagram. It's a nice way to basically display intersections between variables. So remember, we talked about this when we talked about partial correlation in chapter 15. Basically, if you have 2 populations, those that have used Airbnb in the past and those that have never used Airbnb. So you have here some aspects which are specific to either population. So travelers who have never used Airbnb, they will be concerned about security, service quality, and housekeeping, whereas travelers who have used it in the past, they know to look for location, amenities, past experience, and loyalty. And there are some intersecting joint aspects. So now, when you think of that in analytic terms, you would have a questionnaire, and like individuals would need to rank what's really important to you and what's not important to you. So this is how you would depict those responses. And then the end of the day is you have here 3 different categories with this overlapping category basically being intersecting between both groups, both populations, and you would depict this with percentages, for example. That's one way to depict it. You can also build Venn diagrams where the intersect gets smaller if the percentage is really small. So there are various ways how to depict So we talked about open data practices. Next to pre-registration, you should also report ethical data practices that you used after they collected the data. So it's not only the pre-registration, which is basically shown here with that check mark. Then you also should have open data. So that's a debatable point. It's like, so, yeah. So when you submit your paper to a journal, journals deal with that differently. Some journals require you to actually submit your data, and that will usually be in the format of a de-identified data set. So you actually find nowadays with many journals, you find a lot of data published. So you have like data reported from a randomized controlled trial. You can download the actual data that the authors have analyzed and collected from their subjects. I have a couple of examples for those of you that are interested. So that's open data. However, then there are also other journals that let you get away with, we cannot publish the data freely, but upon request, we will accommodate additional analysis. So there are various approaches to that. Open material, same concept, but now it's really coming towards, I want to see additional analysis of your data, or I want to know which code did you use? How did you code your analysis, and how does that look like? Many journals, again, particularly when it comes to more complex methods, where you basically develop a mathematical model and you're publishing that mathematical model, they will want to see that code that you have produced. And they want this to be published online, and they will request this from you when you get your paper published. So that's open materials. And that's the end of this. Any questions on chapter 18? I think it's pretty much a recap of what we've discussed already. So it's a nice way, it's a nice comprehensive way to put this all together. So if no question, then we can actually go for the next 5:24. We have 30 more minutes. Then I would just cross-sectionally quickly jump through all the that one. Briefly just jump through all the slide decks. That should go quick. So chapter 1. Remember the difference between descriptive and inferential statistics. I've just seen that on this quiz, actually. I've seen a rather unsatisfying response to the question. So descriptive statistics is really where you organize, summarize, and communicate groups of data to your reader. Whereas inferential statistics, you are digging deeper, and you use your data for decision making and hypothesis testing. And this is basically where we're getting into the statistical methods that we have discussed in the following classes. Well, know the difference between populations and samples. I think that's easy. Know the difference between discrete or categorical variables that can be nominal, ordinal. Then know continuous variable. Know the difference between interval and ratio. Stroop test, we talked about that. Well, flagging the cookies. Remember the cookies. So that's basically the simplest way I could envision of how you can basically distinguish between these four groups. You also, and this is important, you can take continuous data and you can quote unquote discretize this data by basically binning it into categories, which we've done in a way with a histogram, right? So histograms can be a population density plot, which is this smooth line that we see in the slides, or it can be bins. Like it becomes almost like a bar chart depicting the entire magnitude of data. Well, make sure that when you read a question that you distinguish between dependent, independent variables and confounding. Also saw some shortcomings there. Make sure to review that. What is confounding? What is the third variable? Think of ice cream consumption and death from drowning. What could be the confounding variable? Reliable and valid. Know these differences. Hypothesis testing, operational definition of variables. That's also important. Yes. That's the first one. I also recommend download all the PowerPoints and have it handy in a folder on your computer. That you're just faster, that you're faster to find that information in case you need to look for it. Preferably you don't have to look for it, but if you have to, have them handy somewhere. It is 70 minutes, which is a decent amount of time. So that's you won't be in a rush, but you can be in a rush if you don't find the information that you need. Operational definitions are basically where you need to develop the framework of what is a dependent variable, what is an independent variable, and on this information provided in the question, how do I operationalize and how do I find out what is the independent variable and how I'm going to use it. This slide indicates that quite nicely. So basically, if I study levels of happiness and my independent variable is pet ownership, then what is the conceptual variable? What is the dependent? Dependent is the level of happiness, but pet ownership makes you happy. That becomes the independent variable. What's the confounder in something like that? Yoga, exercise, antidepressant medication. Who knows? But it's basically keep in mind how you look at these things. Correlation is association. We know that random assignment, an experiment. So you have observational research and you have experimental research. The difference is that in experimental research, you have some form of intervention. You have something that you are doing with these subjects, and you're placing an intervention. And based on this intervention, there will be a change in your dependent variable. The assignment to the group here is your independent variable. So if it's in a control group, then you basically have that individual assigned to one group. The intervention group is the second level of your independent variable. Why random? Because you want to minimize or eliminate, preferably, the effect of confounders. So if you're testing happiness and pet ownership, let's say, well, you give everybody a pet and the other group doesn't get a pet, right? So essentially what could be the confounder, that could be level of antidepressants. So now you want to create two populations that you're studying that are in either level of this independent variable, and you want to have an equal balance of people taking antihypertensive medication. So that's kind of the idea. You want to balance your confounding variables and thereby minimize the effect of the confounding variable on the effect of your intervention. That's the idea. That's why you randomly assign to either group. Health behavior, that was a good one. Yeah, between groups, forcing groups design, talked about that. Data ethic, open science, we just talked about that. Yeah, problem with not just with psychological science, just generally with science, replication. Particularly from non-randomized research and research that is observational in nature, you often you cannot establish causality without randomization. But you can kind of assume some form of causality, and you're doing that by replication, most and foremost. That's, you repeat it 100 times, and you have 100 different surveys and 1,000 people. At the end of the day, after 100 surveys show the same result, you can kind of assume, okay, there may be something in there that is causally related. So there are 11 criteria posed by Bradford Hill that in the 80s. The 70s that essentially give you criteria with which application you could assume causality to your findings. But these 11 need to be met, or at least a majority need to be met, replication being one of them. So, but this is the problem that you have with many studies, particularly underpowered small studies with questionnaires that are not reliable and valid. You have replication failures. That means you're doing a survey in 100 people on campus, then you have your colleague take the same survey and do it at home, and wants to leave home for the semester, and they do it in the city they grew up in, and they find an entirely different result. That's a replication failure, likely because of poor sampling. Problems with data collection also quite frequently found. Wrongly collected data, poorly administered questionnaires, poorly assembled questionnaires, wrong mode of collecting this data. So there are various reasons. Old-fashioned statistics that don't really get to the bottom of the dynamics that you want to report. Data ethics, pre-registration, we just talked about, and harking, hypothesizing after the research are known, which is basically a fishing expedition and then building a hypothesis after you know the results. So that's chapter 1. And that's quite a nice and important general chapter. I just want to repeat those because that was quite a while ago, so that may not be totally fresh in your memory. Frequency distributions. That was the next chapter. So frequency table, group frequency table, frequency histograms. That's simple, right? It's like we talked about this. We did the volcano example. Distinguish between a raw score and a frequency distribution. Know how to distinguish those. Know what then the depiction as a frequency table basically shows, how you can use that, and how that basically could be converted into a histogram. Know what a grouped frequency table is. So remember the frequency table example with the volcanoes. Then we have a grouped frequency table that basically just works them together and builds bins of different levels of the independent variable. You just have groups that you're depicting now. So you zoom out and you look at it with less granularity. Histogram is basically a bar graph that shows each individual point on your x-axis and shows you the frequency of that. So basically, if you have a bar graph, the characteristic and the distinction between an actual bar graph is that a histogram, you spread the entire range of your continuous x-axis or your continuous x variable, and the bars are right next to each other. And it's usually overlaid with a frequency density plot. So this is the histogram. That would be a density plot. So that basically takes the frequencies and basically builds a mathematical functions for it and just shows it in a smooth way. Distributions, forms of distributions with normal distributions, which is bell-shaped, symmetric, and unimodal. We have a skewed distribution. Don't forget that tail tells the tail. So if the tail points upwards, then it's a positive skew. If it points downwards, it's a left skew or negative skew. Floor effect, ceiling effects is when it ends. The classical example with a floor effect is exam grades. Basically, you have a maximum of 100. That's where it ends. And then you have classical floor effect is median household income. Basically, nobody can earn less than 0. Well, hypothetically. And so basically, that's the threshold. So that's the start. Know how to distinguish those both, positive skew, negative skew, dot plot. Same story, you show one variable as an individual dot. It's a rather rarity. You wouldn't use it for large sample sizes. Okay, that was a simple one. This is descriptive statistics. So that's important. This is very descriptive. This is descriptive in nature. Then we have the visual displays. Know the different lies. You have positive and negative uses. So the bias scale lie, basically where you have scaling to skew the results. Discontinued axis falls into that. Sneaky sample, which is, I'm not sure that's typical to a graph, but we had this conversation, right? So it's pre-selected or self-selected to provide data. So you can, that also includes the inaccurate values lie in essence. Well, essentially it's removing outliers would fall into a sneaky sample in a way. Interpolation, extrapolation, know the difference. Inaccurate values is scaling where distort portions of the data, as we have seen later on. Scatter plots. Scatter plots is basically what you would always do first before you do any form of correlational analysis. So you have a dependent variable, which is the outcome variable that you depict as a function of your independent variable, you basically, you do this first because you want to see, is there some form of relationship? Does your dependent variable indeed increase when the independent variable increases? Or does it decrease when it increases? So is it a positive or a negative relationship? And if so, is it linear? Because if it's not linear, then give up on Pearson correlation and regression. Well, at least at the univariate linear regression that we have done. Also, some of you may have seen on the quiz, and I gave you those points, the distinction between bivariate and multivariate regression. I didn't really feel that this question was appropriately graded. I've removed this question now, because if you have two variables and you have a quote unquote univariate regression, you basically have a bivariate regression. So that's just, it's splitting hairs at this point. Okay, linear relation, nonlinear relation, line graphs. Only use line graphs when you have a chronological dependence. So when you have time depicted on the x-axis, then you do line graphs. If you have a scatter plot, never connect the dots. Just don't do it. Only if there's an additional dimension of time involved. Line of best fit is basically a fit that means to minimize the distance between the individual data point and your predicted data point. So you want to minimize the so-called residual. And by doing that, you minimize the squared deviations. That's why it's called a least square approach. This is a time series plot. Characteristically always shows data over time. Yeah, we talked about this. Very powerful graph to interpret. Then we have bar graphs. So the height of the bar typically represents an average or a percentage. Usually also as a mark of variability. So if you have a mean, you can also depict the standard deviation on it, which is usually elegant to do. We've used it in the context of chi-squared. So when we had the paper cup example for chi-squared, we used it to depict percentages, if you remember. Pareto chart is basically a bar graph with ordered magnitudes, but that's pretty much all to it. Example here is internet users that use Twitter. Bar graphs are nice to show percentages. You can deceiving with the scale. Always make sure that you understand the scale. So if you have here a discontinued scale, don't get tricked by it. Pictorial graph, yeah, that's just ridiculous. Then we have pie charts. Do never use pie charts to present percentages. Always favor bar charts over pie charts. Reason for that is, even if you write the numbers in it, it doesn't really give you a good means to compare the respective groups to each other. So one scale variable is histogram of frequency polygon, one scale independent variable, one scale dependent variable. Scale is scatter plot, or line graph if the independent variable is time. One nominal or ordinal independent variable and one scale dependent variable is bar graph or Pareto chart. Two or more nominal or ordinal independent variables and one interval dependent variable is a so-called bar graph. Talked about this. Okay. Yeah, know how to read a graph. So there are graphs, and some of you have seen them already on the quizzes. So you will need to read, understand, and interpret graphs. Be prepared for that. Understand which variables are depicted. So I would almost like write it down. Write down what you see on this graph, and then think about it. What is the dependent variable? What is the independent variable, and why? Why do you look at this graph? What was the motivation for the researcher to build this graph? Is the dependent variable nominal, ordinal, or scale? What are the units of measurement on the dependent variable? Understand the units. Which variables did the researchers use to predict this dependent variable? What is the independent variable? What's the nature? What are the levels? And then basically compare those magnitudes and try to draw inferences based on these magnitudes and the differences between the respective categories. Yeah, the guidelines, Moiré vibrations, grids, and ducks. Don't create graphs like that. And also know the future of graphs and the various different advanced graphing methods that are out there. Yeah, bubble graph, that's a multivariable graph. No? Yeah, so we know central tendency and variability, that's easy. Mean, median, mode. No, that basic thing that I keep on talking about is like the arithmetic dependency of a mean to each individual data point makes the mean most sensitive to outliers. You're changing one variable and you're increasing that variable by a couple of percent. If you don't have an enormously large sample size, you will likely see a change in the mean, whereas the median will only change if you change a decent amount of different variable of entries. So the mean very sensitive to outliers, the median not so much, the mode not really sensitive. So know the difference, know when to use a mean and when to use a median. Normally distributed data usually can be nicely shown with mean and standard deviation. If you choose to show data with a median, traditionally you show it median and 25th and 75th percentile and IQR, not the standard deviation. Traditional, that's done that way. I would resort to both. Because if you compare mean and median, you can kind of hypothesize about the nature of the data. So you know already in which direction the tail pulls the data away. So we talked about all of this. We talked about this before. Greek annotation indicates population. M or X bar indicates statistic. The different model distributions, you have unimodal, bimodal, or multimodal. Yeah, we talked about all of this. You have range, variance, and standard deviation. So know the difference. Know that essentially what you look at when you look at the variance, this is the average of the squared deviations. So basically you have, if you add all the squared deviations up, you have the sum of squares. If you divide those all by your sample size on the population level, you divide it by the sample size, you get to the variance. If you divide it by your degrees of freedom in the sample, you also get to the variance. If you employ the square root on the variance, you get the standard deviation. Range is highest minus lowest, we know that. Understand the percentiles. So 25th percentile indicates that 25% of all your data points are below that. The median is consistent with the 50th percentile, so that's splitting your sample in half. So 50% are below that threshold and 50% above. If you go to the 75th, you have 75% of your population below the threshold and 25 above. So there may be some questions which kind of test on your understanding of that. And it becomes also important when you think of a set score table, because you find these percentages reflected in your data. Q1, Q2, Q3, Q2 being median. No, wrong. Median is the median of all scores below the median is the first quarter, so that's Q1. Then we have Q2, that's the median. So we have Q3, that's the median of all the data points above the median. So that's like splitting the upper half into half. That's Q3. Now with variance, we did that quite excessively. So that's central, that's mean and variability. Then we have here sampling and probability. Are there a specific chapter that you want to repeat? Or should I just keep on going because we're running out of time? That's what I'm asking. If there's a specific chapter, let me know. The sampling probabilities, so basically you have random samples and convenience samples, which, yes.
Go over Z-scores.
Z-scores, yeah. Okay. Okay, random sample, convenience sample, I just run through this, then I'll do Z-scores next. Random samples never used because it's not feasible, right? It's literally not feasible to do random samples. That would imply, that would imply that every member of the population has an equal chance of being selected into the study. Random sample is nearly ever the case in research. Also in your questions, if not. Convenience samples are mostly what most studies are being conducted. No, when it comes to convenience samples, the downsides, and the number one downside is generalizability or external validity. You will have problems comparing this to the overall population. Can be improved as replication, but it still is a downside. Don't believe testimonials. Random assignment takes off confounding. There's nothing to do with sampling. Probability has nothing to do with sampling. Probabilities, know how to calculate probability. So there may be simple questions about probability, but nothing too detailed. Probability is successes over trials. Remember the 10% diabetics, where you randomly choose individuals on the streets of New York. Inferential statistics, hypothesis. We talked about this, null hypothesis, research hypothesis, reject, fail to reject. You know all of these. No type 1 and type 2 error. By all means, know the difference between those two. Okay, Z-score. Was chapter 6. So Z-score is something that you only look at in a population. So also the Z test is only done in populations or when you compare samples where you have standard deviation and mean given to population means. What you're essentially looking at is a normal curve and the standardization of that normal curve, because since it's symmetric, you're utilizing that property that if it's symmetric, it will extend in both directions at the same time. And the middle, the mean, is exactly 50%. So it's symmetric and bell-shaped. Sample size. What you do with a Z-score is essentially you are assigning a generally applicable standardization scheme to a normal distribution that uses the mean and the standard deviation of this distribution of that particular population that you have at hand to characterize it. And that means that if you have a population where you say, okay, so a certain fraction of my population is overweight. Let's do a certain proportion of my population is diabetic or hypertensive. And you're basically determining some parameters. So I have, let's say, 20% of my population is has very high blood pressures. You can take the same dynamics by quantifying that Z-score. You can go to a different population and you can employ the same dynamics with the respective population mean and standard deviation. And you can, by standardizing this population and comparing the standardized value to another population, you can compare populations to each other. Or you can compare your sample to a population with a Z-test. So basically you are standardizing it by saying, okay, so you have a normal distribution, you have a mean. At that mean, my Z equals 0. If I have my standard deviation of this population given, I capture 68% of my population within one standard deviation above and one standard deviation below my mean. So within 2 standard deviations around that mean, I have 68% of my population. So this allows you to estimate your entire normal distribution and your entire population, although you may not know every individual entry, but you can use it for the estimation of each individual entry. And the standardization is done by basically calculating individual set scores. And what you do is you calculate individual data points minus your mean, and you get the distance from that mean, which is either negative or it's positive. And by dividing it by the standard deviation, you're giving it the distance from the mean expressed in the number of standard deviation from the individual point to the mean. And that can be a full number, that can be one, like with one standard deviation below or one standard deviation above, or this can be less than one, or this can be more than one, this can be a decimal, this can be a decimal with 3 decimals. But by getting this calculated in that shape or form, you always get the distance expressed in the number of standard deviations it's located away from the mean. If it's a negative value and it's smaller than the mean, your x, then it will be a negative set. If it's greater, it's a positive set. Do you want to go over the set score table too? Yeah, well, 2 minutes. Plenty, but no. No. So that's the set score table. I know how to read those tables, right? I've given them to you. So again, so you have here this little bit complex looking table. That. Looks a little bit complicated, but basically at 0, you have 50%. So you have 1 decimal and the full number here on the columns, on the now on the rows. On the columns, you basically have the second decimal. So at 0, you here have 50%. If you're going up now and you want minus 0.04, you're essentially seeing here 48.4%. So this is 0.4 standard deviations below the mean. And this basically 0.04 standard deviations in that small little pattern below, you have 50 minus 48.4. So you have 1.6% in 0.04 standard deviations. So the standard deviation here really becomes your unit almost. And where it's becoming really interesting is now when you look at 1.96, where you have 2.5, because these are the tails that are being used to determine the alpha. So this is plus 1.96 for the right part and minus 1.96 for the left part. And these need to be considered symmetrically. So when you're standardizing your difference between your sample mean and your population mean, you're standardizing these differences in the end of the day, and you want to know whether that difference is actually significantly differing, and that difference is actually small, exceeding a 0 difference by more of your critical thresholds. Any other questions? Well, if not, then utilize the discussion board in case there are additional